Can you hear me and see my screen?
Yes, we can.
Okay, thank you. As usual, mark your attendance first. So once you're done with that, the plan for today is to firstly go through some of the quiz questions for your quiz 2 last week. Generally, the mean score is pretty good. However, I have 3 questions where many of you got wrong. So the first question is this question, right, which I was quite surprised that many of you got it wrong. In fact, there's only 1/5 of the class that got it correct. Okay, so I'm firstly going to go through this question first. Then subsequently, I'll go through another question, another 2 of the questions whereby the chain rule has not been applied correctly by some of you. Okay, so firstly, we'll go through the 3 questions for the quiz 2 today, followed by we'll finish up differentiation applications 1. Okay, then we'll definitely start on applications 2. So that's the plan for today. And this Friday, you will not need to hand up your homework 8, right? Because I've not gone through, I have not finished the differentiation applications 1 yet. Okay, so I'm going to postpone the handling in of the homework 8 to next Wednesday, so that you have more time. Okay, at least 1 week to complete your homework. So let's start. This question asks us to determine the derivative, which is the h prime, right, of the function h here. So therefore, this g of x is clearly just a function of x, just another function of x. So therefore, to differentiate this, you can see that this is a function of x over another function of x. So I think most of you are able to do the quotient rule. So if you make use of quotient rule, right, you must hold the denominator first, multiply by the numerator differentiated, so g prime x, minus differentiate of the denominator. But this is actually kx to the whole thing to the power of half. So therefore, you get 1 over 2, then the half minus 1, you get minus half, right? So you have a square root of kx, okay? Then not to forget, you have your chain rule. So therefore, differentiate kx with respect to k, you have a k. Remember to put back your numerator without differential. Then this whole thing divided by the denominator squared. So divide by kx. Okay, so I think most of you can get this. I don't know. Maybe some of you forgot to use chain rule here. Okay, because this is what happened for the other 2 questions as well, right? So subsequently, once you get this expression, right, you just need to factorize out square root k and you get the answer. Okay, because obviously you can see that this is just square root k times square root x times g prime minus this guy. You can see there's a k here divided by square root k here, right? So you're just going to get a square root k over 2 square root x times g of x. Okay, so of course this is power 1, right? This is power half. So therefore, numerator has power half. And this is over kx. So therefore, if you factorize out the square root k, and then you divide off, so you're just going to get square root k. Then this is just the same stuff. Then minus, then this guy is g of x over 2 square root x. Then subsequently, this is over kx, right? But over kx, I can put it here. Okay, so I put a big bracket here. So you can see this square root k divided by k. So hence, it is quite clear that you get 1 over, and this one just put a square root. So hence the answer is 2. So this is the answer, option 2. Any questions? So if I did not guess wrongly, it's either the 4/5 or 80% of you got it wrong, right? Because you did not, I think you might not have factorized out or remembered to apply your chain rule for kx. Okay, so without this k, I think you're going to get one of the other answers, right? And the other possibility you got it wrong is because you didn't manage to simplify into this form. So that's the correct answer, option 2. Okay. So if you have no questions, I move on to the next question, which I think about a third of you got it wrong. Okay, a third of you got it wrong. So this question is worth 2 marks, but it's actually quite straightforward. So if you look at this, it's actually a exponential function. So it's a constant base 2 to the power or to the exponent of a function of x, right? So therefore, this will require you to use your differentiation, if you still recall. So f prime x, right? If you still remember, before you look at f prime x, we are actually using the differentiation. Let's say, for example, a, which is your base. Okay, let me just put this as b. Okay, so base b. So base b, right, to the, let's say, power of x. Now, you know that from your differentiation rules, and we have derived this before using implicit differentiation. So this guy actually will give you b to the power of x ln b. We put ln b as a constant in front first. So you get ln b multiplied by b to the power of x. Okay. However, if this is slightly more difficult, like b to the power of some function of x, let me put this as gx so that we don't mess up with this fx here. So what we have, right, is actually still ln b, but b to the power of x or b to the power of gx. Then subsequently, you must have your g prime. That's your chain rule. Is that all right? Okay. So therefore, if you look at this expression, it's actually applicable to this f prime here. So therefore, to get f prime, right, you just need to apply this green part. Okay, because this is really just 2 to the power of some g of x, as you can see. Okay, but g of x is just a function of another function of x. So you need to have a chain within a chain. So let's see. So hence, no big deal. Just write down the ln b first. That's a ln 2. Okay, since your b is 2. Then subsequently, you have b to the g of x. b to the g of x, just copy down the whole expression again. So now you have to differentiate this g of x. Okay, sorry, differentiate this guy. Okay, so this guy is your g of x. So let me change this a bit so that you don't mess up. Let me change this to h. Okay, because you mix up with this g later on. So therefore, let me change this to h. Okay, no big deal, just change of alphabets. So this whole thing is like h. This whole exponent, right, is like h. So now you want to do h prime. So what's a h prime? Differentiate tangent inverse. So when you differentiate tangent inverse, let me just put it below. So you're going to multiply by one big chunk, 1 over 1 plus gx squared. Okay, the square of g of x. Then subsequently, you need to differentiate g of x. That's a chain rule. Is that all right? Okay, so basically this term h prime here, right, is actually this guy. This is representing your h prime. All right, I suspect once again most of you or some of you who got this wrong, right? You forgot this g prime. Okay, that's my guess. So therefore the answer here is option 2. Okay, after you multiply everything together, let me just check. It's a ln 2 here. Yeah, that's correct. Questions? So the trickiness here is actually the chain rule within the chain rule that you need to consider carefully. So hopefully you are good. So last question for the quiz. And once again, I think I think a quarter to 1/3 of you got it wrong. So once again, by implicit differentiation, determine dy dx. Okay. So this y is actually a function of x, as stated here. So this is an implicit function. So therefore, you have to use implicit differentiation because we can see we are not able to explicitly isolate the y in terms of a function of x. So we perform implicit differentiation, okay? So we just d dx, both sides. And we get e to the cy, right? So therefore, just c e to the y, okay? Differentiate e to the cy with respect to y. Then whenever you differentiate respect to y, you put a y prime. Okay, that's your chain rule. So that's good for the left-hand side. Then for the right-hand side, obviously you got two terms, okay, or two functions of x. Bx multiplied by y as a function of x squared. So hence, you're going to use your product rule, right? So of course you can factorize out the b first, it's a constant. Then multiply by differentiate x, so you get 1. Then hold your y square, plus your product rule kicks in. So therefore, differentiate whole x, differentiate y square. So therefore, you get 2y times y prime. All right. So once you have this form ready, you just need to isolate your y prime. So clearly, if I bring my y prime, let me see my answer. Okay. So just bring this across. So you get CEY minus 2xy times y prime, right? So factorize out the y prime. Okay. Now, of course, hold your remaining terms on the right-hand side. By squared. Right. So y prime must be equivalent to by squared over this whole thing. Just divide throughout. Okay. So therefore, you can see that this answer is actually, oh, of course, I forgot to multiply by b here. Okay. So by squared, there should be a b. This b multiply inside, I forgot that. So therefore, let me just plug in my 2b here. Okay, b times 2xy prime. So I have my b here. So that gives, oh, I forgot my c here. I differentiate, bring down the c. This will still be a cy. Okay, so cy. So the answer is option 1. Questions? Okay, so I hope for those who got the 3 questions wrong, you are better now, okay, at understanding the chain rule. So the chain rule is to be used extensively. In fact, today's lesson in linear approximation, we are still going to use the chain rule again, as well as in related rates of change, also the chain rule. Okay, that's why when I introduce the chain rule, I say it's the most important rule in differentiation. So we're going to dive into the related rates now. So I'm just going to continue our applications 1. So it touch on some of the applications, radioactive decay, population growth, as well as Newton's law of cooling already. So I'm just going to straight jump into related rates. Let me get back my chat box. So as the name suggests, related rates means when you have a relationship between two variables. So when you have a rate of change in one of the variable, how does the relation between those two variables translate into the rate of change for the other variable? Okay, so that's why it's called related rates here. And I can give you some examples. So let's say, I'm just going to straight away use the example here. So let's say you have a balloon, right? And balloon is filled with air. Okay, so let's say this balloon, right, is inflated such that it maintains its spherical shape. So it is possible that we know what is the rate of inflation, which means we know how much volume is actually being pumped into the balloon per second. Okay, so which means that we know the rate of change, right, in the volume here. Okay, so therefore, if we know the rate of change in the volume here, right, then we ask, what is the rate of change in the radius of the balloon? Okay, so obviously we know that the volume of the balloon is related to the radius of the balloon by the volume formula of the sphere. Okay, so we can see that, for example, so like V is equivalent to, or rather V of T of the balloon is actually equivalent to 4/3 pi r cube. Okay, so this 4/3 pi r cube is nothing, just the volume of the sphere. Okay, formula for the volume of the sphere. And we can actually derive this using integration. Okay, as you will be doing in your calculus 2. Okay, so now this 4/3 pi r cube, right? You can see that when the volume changes, 4/3 pi is clearly a constant. So that implies that this r must change, right? Or else this v cannot possibly change. So therefore, this r is actually a function of time. Okay, so now our understanding is, well, if you know what is the change in dv dt, then can you actually relate this dv dt or v prime to r prime? Okay, so I think some of you may have observed that you can actually just differentiate and then use your chain rule in the process, and you will be able to derive the relationship for r prime in terms of v prime. Okay, so therefore the chain rule is being extensively used here once again. So these are further examples that I will not go through. You can read them yourself. So there are actually some steps that we use as standard to solve a related rates problem. Okay, so as I mentioned just now, there must be some relationship between the quantities. Like for example, in the volume and radius just now, right? You have to have a formula, okay, that relates the two quantities. So once you have that formula already, then we implicit differentiate, okay, as we have done just now, right? It's possible that you have explicit differentiation of as well. For example, if you know your volume as an explicit function of radius r, right, then of course you can just differentiate explicitly, okay? But if not, then of course you can still do your apply your implicit differentiation. So once you do that, right, you'll be able to get a function or equation, right, involving the two rates of change. Okay, and it is possible here that you get more than two rates of change. All right, as you will deal with some examples later on. So once you have this, right, then of course you can set up, or you can isolate your unknown, such as dy dt. Let's say you're given dx dt, right, and you want to find what is dy dt. So you just isolate your dy dt, then subsequently plug in the given values at a particular time. Okay, and these values, right, may not be complete. So you may have to establish some other relationship to find other unknowns. All right, because eventually when you differentiate this relationship, right, you have only one equation. So one equation can only at most solve for one unknown. Okay, so if you have more than one unknown, but you have only one equation, which probably implies that there is another equation that you need to develop. All right, so we'll look at some examples later on that contain such complication. All right, so just 3 steps. So in many of the examples that we go through here, right, we will look at some of the so-called volumetric changes, right? So these are the standard volume formulas that I think we should know. Okay, so all of them can actually be found by integration. Okay, which I will not go through here, of course. So this is another formula whereby we have the concept of similar triangles. Okay, so similar triangles is just the ratio of the lengths are equivalent. Okay, so if you look at, for example, this small triangle here, So you can see the ratio of this R to this 8 is actually similar to the ratio between H and 20. Okay, and of course, you might notice that this actually comes from what? Comes from trigonometry, right? Comes from trigonometry. Predominantly because the angle theta here is a constant. Okay, so therefore, if you try to relate the opposite to the adjacent, right, then it's pretty clear that tangent theta could be given by two expressions, right? Opposite R divided by adjacent H. But this tangent theta can also look at the bigger triangle as well. So therefore, this has to be 8 opposite adjacent 20. So clearly, this is actually representing your ratio, okay, or equivalence of the two ratios. So therefore, if you just cross multiply, you're going to this expression here, okay? So it doesn't matter how you write it. For similar triangles, right, you can always write it in terms of this form or this form, okay? Both are definitely correct. So here's the strategy, but I'm not going to go through step by step. I'm just going to demonstrate through the examples. Okay, so let's say you have an example here, right, whereby it's not explicitly clear. Hold on, it's actually here. So we have a ladder that 5 meters long and rests against a vertical wall. So if the bottom of the ladder slides away from the wall at a rate of 1 meters per second, how fast is the top of the ladder sliding down when the bottom of the ladder is at 3 meters away from the wall? Okay, so of course, you can observe here that as this guy is moving towards the right, then this point here is actually sliding downwards. Okay, so let's go through the steps in this example. So first of all, we make a drawing, right? If you can make a drawing, you make a drawing. Okay, try to make some maybe representations that allow you to formulate the relationship between the variables more easily. Then subsequently, use letters to represent the variables involved. And the variables involved, right, typically one of them will be what is being asked explicitly in the question. Okay, so for example, the question here, right, it is actually asking for how fast is the top of the ladder sliding down the wall. Okay, so when we say how fast, right, it's actually a velocity, right, which means that if you think about it, you actually want the velocity of this point sliding down. So this velocity is given by v in the y direction, right? V in the y direction. But we know that v in the y direction is actually equivalent to y prime of t. Y prime of t. Is that right? Okay. So therefore, we relate this variable y prime, right, to another variable that we might know. Okay. In this case, as you can see here, is obviously this x prime here. Okay. So at this point, this guy is actually sliding towards the right, and you can see that this guy is actually my x prime, which is my velocity in the x direction. So that's for step 2. So use letters. Okay, so in this case, it's quite convenient to use this dimension will be the y from the ground, and this dimension will be the x. Okay. So therefore, we are supposed to find this y prime here, right? dy dt, what is this, right? When x prime is actually 1 meters per second, okay? And it's important to take note of the polarity, okay? It's important to take note of the polarity because this x, when it's sliding towards the right, this x is increasing. I repeat again, when this x, this point, is sliding towards the right, x is increasing. So therefore, when x increases, it's going to be a positive polarity. Okay? So dx dt 1 meters per second, right, is because of this x is increasing. So therefore, this has to be a 1. All right? Now, this dy dt, you have to consider also. If this is y, then when this point is sliding down, this upper point is sliding down, you have to consider that this is actually y prime being negative. Okay, because this y is decreasing. So let me draw the arrow here, and you can see that this y prime, right, or y is decreasing. So when y is decreasing, y prime must be negative. Okay, so therefore this dy dt here, you should expect a negative value. Okay, if you can, because this is a relatively simple problem, right? So therefore we try to apply some kind of logic or intuition so that when we get the answer later, right, we are able to deduce whether at least our answer is in the correct direction or not. Okay, so quite clearly, regardless of how much this ladder slides, as long as it forms a triangle, right, with these 2 points on the vertical and the horizontal floor respectively, right, we can actually apply the Pythagoras theorem. Okay, so Pythagoras theorem, x squared plus y squared equals to 5 squared. That's pretty straightforward. So then subsequently, we just do a implicit differentiation of this Pythagoras theorem. So this part is easy. I'm not going to go through. So therefore, you get y prime equals to minus x over y x prime. Okay, so you can see the relationship between x prime and y prime here, right? So therefore, what is the given information? The given information, right, is actually, it is telling me that the point x is actually sliding away from the wall, and then the given information numerically is actually when x is equivalent to 3 meters, right? So when x is equal to 3 meters, I do not know actually what is x prime. Okay. Oh, sorry. I know what is x prime because this is actually x prime. Okay. Bottom of the wall, the red is here. So I know x prime and I know x. So therefore, I have two knowns. And then now I can substitute into my dy dt equation. Okay. So there is no big deal. Just isolate your dy dt and subsequently substitute in x equals to 3, as well as you do not know this y. So therefore, you make use of your Pythagoras theorem. Okay. So that's why I mentioned, right, when sometimes the amount of information that they give is not sufficient, right? Because you have one unknown here, and so therefore you need one more equation to solve for this unknown y here. All right, so of course you have your Pythagoras theorem, and you can just do a substitution. You get y equals to 4. Okay, so let me just put a note here that this is just equivalent to square root of, because this is a 5 square minus x is at 3 square. Okay, x is at 3, so therefore x squared is 3 squared. So hence you can solve for y equals to 4 and subsequently plug into the equation that you have derived and you get minus 3 over 4 meters per second. Okay, so of course this minus sign, right, agrees with our intuition as we discussed just now. Okay, so the top of the ladder is sliding downwards at 3/4 meters per second. Questions on this example? Okay, and not only you can discuss or you can deduce or you can logically or intuitively understand the polarity, you can also compare the magnitudes between dy dt and dx dt as well. Okay, now you notice that this dy dt is actually less than, applying some intuition here, you notice that dy dt, the magnitude, right, the speed at which this guy is sliding down is actually less than the magnitude of dx dt at x equals to 3 meters. Okay, in fact, this is logic or observation, right, of something sliding down when leaning against a wall. And why is that so? Because, right, this triangle is actually looking more something like that. Okay, where this is 3 and this is 4. So therefore, when you have something like that, and this guy is actually sliding down, right? Now, this point, when it moves a lot, this point doesn't move so much. Okay? So therefore, if I use arrows to represent, this point, it moves a lot. This point doesn't move so much. Okay? So if you think about the extreme case, where when the ladder is almost vertical, when this ladder is almost vertical, you can imagine, right? This point is going to move a lot, but this point, right, it doesn't move so much downwards. Okay, so of course, when you have the other way, something like that, then you can expect when this point moves a little bit, this point is going to move down a lot. Okay, and that is actually manifested in this equation here, in our chain rule. Is that all right? Okay, precisely because of this ratio here, right? You can clearly see that when is this equivalent? When are the magnitudes of the sliding equivalent? When x and y equivalent are of equivalent dimensions. Okay, so you get, for example, like in this triangle here, whereby your angle is 45 degrees, right? That means, let's say y is equivalent to some value that is exactly the same as this x, right? So therefore, this is 45 degrees, then this guy becomes 1. Okay, only at that point where you get a so-called isosceles triangle, right? Then you are able to get the magnitude of the sliding in the vertical direction equals to that in the horizontal direction. All right, so I think that agrees with our intuition, or at least our observation of something sliding down, okay, when leaning against the wall. Questions? Okay, good. So let me continue. So let's look at this example. Let me see if I have the answers. Okay, I don't have the answers here, so I'm just going to work this out together with you. So we have a water tank that has the shape of an inverted circular cone with base radius 2 and height 4 meters. So let's draw. So step 1 is always try to draw, okay? So we have an inverted circular cone and its base radius is 2. So this guy is 2 meters and my cone maybe looks something like that. That's really nice. And my height is actually 4 meters. And then my water is being pumped into the tank at a rate of 2 meter cube per minute. So I got water going in at 2 meter cube per minute. So clearly this is a volumetric flow rate, okay? Volumetric flow rate because it's meter cube. Meter cube is actually your volume, okay? And then per unit time, so volumetric flow rate. So find the rate at which the water level is rising when the water is actually 3 meters deep. So when the water is 3 meters deep, right, is somewhat maybe at this level because it's 4 meter, right? So water is 3 meters deep, maybe it's somewhere around here. And then I want to know what is the rate at which the water is rising. Rate at which the water is rising has to be what? Has to be the height. So we want to know, if I call this the h of t, what is actually my h prime t? Any problems with the interpretation? Okay, so now we identify our objective h prime t already. Okay, and then you might have noticed that actually the volume going in, right, is also the rate at which this volume is increasing. So the rate at which this volume is increasing is going to be our v prime t. Okay, so I'm calling v here volume. So therefore v prime t, right, is in fact equivalent to 2 meter cube per minute. Okay, let me just put per minute here for completeness. So therefore, quite clearly, we can observe that the relationship is actually given by the volume, okay, of a cone. So the volume of the cone is actually 1/3 pi r square, where r, right, is actually the radius of this water level here. So let me just draw a representation. So this guy, circular surface. So there is actually a radius here. So let me call that r. Okay, so hence the formula is actually, yep.
You don't want to go to 3.
Okay, so let me continue. So we have V of T, or rather, let me just put volume. So volume of water is given by V, and that is actually equivalent to 1/3 pi r square times h. Okay, let me verify that. This here. right? Pi r square h over 3. So let me go back. Then we use our, so this is our step 1 already, so we found the relationship. Then step 2, so what do? We differentiate. So d dt. So d dt of this equation, right, is going to give us v prime t is just equivalent to 1/3 pi is a constant. So check, this is actually r square h, r square h. So in fact, there are two ways that you can deal with this. One is that you find a relationship between r and h, and obviously there is a relationship. Okay, so you can substitute in the relationship h is a function of r and then have everything in terms of r. That's number one. Another way, right, of course, is to use your product rule. Okay, of course, you can use your product rule when differentiating here because we know that both r and h are changing. Both r and h are changing. Okay, so multiple ways to do this and you can still get it correct if your mathematics is consistent, of course. Okay, so I'm going to do the easier version whereby we find out the relationship, right, between r and h. Then we substitute this r as a function of h, right, into the equation. Then we get v as a function of h only. Okay, then after that, then we differentiate. So either way works. So let me just try out one way first. So you can observe that this cone, right, the angle here is once again a constant, okay, similar to our similar triangle example just now. So therefore, if you have the side view, let me just try to draw the side view here. So if you look at this from the side view, you're going to see a triangle that looks like that. Let me use the same color. So your triangle is going to look like that. Okay, and then you have your level here, right? So therefore, we see that this is h, and we see that this is r. Okay, but however, by similar triangles, we know that this is actually equivalent to, this is my 2, and this height is actually my 4. Okay, so from here, we can see that by similar triangle, so we can write r over h, okay, r over h is equivalent to 2 over 4, okay, the ratio must be the same, right, radius over height, radius over height. So hence we have r over h is equals to 2 over 4. So this is clearly just half. Okay, so hence, this is a simple relationship whereby we get h, oh sorry, I want to express r, okay, because I'm trying to get rid of this guy here. So therefore, r, right, is just equals to h, sorry, h over 2. Okay, and this is actually maintained throughout, right? Regardless of what is r and what is h, this r equals to h over 2 is always maintained, okay, as the volume rises or, declines. So therefore, once you have, right, we substitute into this expression, okay? So I'm going to do a substitution here. And you're going to get 1 over 3rd pi. Then this is h over 2 square. Okay, so therefore my expression here becomes, so this is 1 over 4, right? So this hence is 1 over 12. Okay, 1 over 12 pi h cubed. Any objections so far? Is that all right? So the purpose of doing so is, of course, to get an expression v in terms of h. Okay, because I realized that my objective is to get h prime. Okay, so to cut the story short, I want to get rid of this r here. All right, so that's one way. Maybe I'll show you another way later on, right, whereby you can actually use product rule and get your dr dt as well. Okay, multiple ways to do it. So therefore, this v prime here is clearly just 1 over 3 pi, right? And we're just going to differentiate this guy. Oh, sorry, 1 over 12 pi in this case. So 1 over 12 pi. And this h cubed, right? There's going to be a 3h squared times h prime. Okay, using our chain rule. Right? So I hope you're fine so far. And So to get our unknown, just h prime. So just going to isolate h prime here. So h prime is equivalent to, so this is 3 over 12, right? Now quite clearly I can just simplify terms here. So I'm going to get this 3 strike out, and then this 12 becomes a 4. So therefore my h here really will be given by, let me see, just check for me. So I should get 4 over pi. So I should get 4 over pi. 4 over pi v prime, right? Then I have h square here. So pi h square. 4 over v prime pi h square. Questions? Yep, that is correct. Okay, so once we know this, right, actually we can just substitute our values in already. So we know v prime, which is this guy here, right? And we need to know h. But however, we can know h quite easily because you can see that h is actually given to be 3 meters deep. Okay, so let's have, therefore, straight away right So therefore h prime is actually equivalent to 4 v prime, which is in this case 2 meter cube per minute. So therefore h prime will be in minute later on, right? Divided by pi and multiply by 3 meters. So therefore this is 3 square. So you should get 16 over 9. Oh, sorry, 8 over 9. So it should be 8 over 9 pi, 8 over 9 pi meters per minute. Is that right? Questions? All good? So it looks like you're fine. And I'm going to show you another way. Okay, let's say you didn't realize that, or you didn't convert this R into H. Okay, and make this V as a function of H. So you let this be R. Can you still get the same answer? The answer is you can, right? So let me just do a quick alternate method here. Okay, let me use orange. So check. This guy is actually V equals to 1/3, or let me just put it as pi over 3, R square H, right? So you have something like that, you can clearly get V prime. So V prime is actually differentiate respect to time. And we get V prime, right? Use your product rule. So let's say at this stage, right, you didn't realize to get, replace R. So therefore, now you have clearly in this case 2RH plus 2RH plus H. Oh, sorry, 2RH, my fault. It should be 2R prime, okay, times H, right? Because differentiate R squared respect to R, multiply by dr dt. You can see that, okay? So therefore 2R, then R prime times H, this H must be there, plus, then now you keep the R square, differentiate H, so therefore it's just H prime. Okay, so of course this is just product rule, right? So of course you get a more complicated looking expression here, but you can still do it. You can still do it, okay? Because from here, obviously you want to know your R prime, okay? However, you can actually replace your R prime by H prime. The reason is because you check this. This is actually R equals to H over 2, right? So once again, if you know this R equals to H over 2, then you can differentiate respect to T also, what? So if you have d dt here, you're going to get R prime, right, is equivalent to half H prime. Simple as that. Okay, just differentiate both sides by with respect to time. So just r prime equals to half h prime because half is constant here. Okay, so once you know this, actually you can substitute this into this expression to make everything in terms of h prime. So let's do that. So just substitute into here. So hence you are going to get, this guy is just going to get equals to, so pi over 3. So this is 2r. So 2r. And you can replace this r if you want also. Okay? So therefore, maybe just let me replace everything. So hence you get, let me see. Yeah, so you get 2h over 2. Then this r prime is actually this guy. So half h prime times h plus r square, right? Just h square over 4 times h prime. Exactly what you want. Okay? So from here, it looks like a handful here, but you can actually simplify terms quite easily. So we have this cancel, cancel. Then we get, let's factorize out our h prime. So we get pi over 3. H prime is something that we want. And then this really just leaves h over 2. So h square over 2, in fact. Okay, the first term, so h over 2, then times h here, right? So h square over 2 plus h square over 4. So this awfully looks like pi over 3 h prime, right? Then this guy is actually 2 over 4, right? Correct? So 2 over 4 plus, so it's actually 3/4. So 3/4 h square. Okay? So therefore you strike this 3 off. So you're gonna get pi over 4 h square h prime, or h prime h square. Okay? So in fact, this is our v prime. All right? So you want h prime. So h prime is clearly just 4v prime over pi h square. Isn't this the same as this guy? You just use. You see? This and this is the same. You see? Okay? So therefore, same as previous. So therefore, you can just substitute in the values and get the answer. Same as previous. Questions? So it really doesn't matter when you substitute. Of course, this is a bit better, okay, in the sense that it's more direct, okay, because you express v in terms of the unknown h, or h prime where you want to find. Okay, so this is a bit more tedious, but the maths is still consistent. Okay, so that's why you can get the same answer as well. Questions? Looks good. Let's proceed on with more examples. So now we have a car A that is traveling west at 90 kilometers per hour. Car B is traveling north. So step 1, draw. So traveling west, let's assume north is upwards, so west is towards my left. So let's have car A. So this is my car A, traveling west at 90 kilometers per hour. And then I have car B that's traveling north at 100 kilometers per hour, both headed for intersection. Okay, fair enough. So therefore, this is car B. And this guy is traveling north at 100 kilometers per hour. So hence, at what rate are the cars approaching each other when car A is 60 meters and car B is 80 meters from the intersection? So I think this awfully looks similar to the one where we have the ladder sliding. Okay, but it's just that they are different, they're asking for different stuff. Hold on, let me just move this guy a bit. So heading for this intersection here. So clearly we want this distance. Okay, this is the distance that we want, right? At what rate are the cars approaching each other? Okay, so which means if we call this D, right, we want this D prime. Okay, because it's rate, right? So the D dt lah, in the sense. So hence, we are given that this car A is 60 meters, okay, and car B is 80 meters from the intersection. So that's the two distances known. So quite easily, we can just treat this as y. So we're going to call this distance y. And we're going to call this distance x. All right. So by Pythagoras theorem, we get x squared plus y squared equals to d squared. Okay, of course, when x and y are changing, right? X and y, they have their own rates of change. And then it's going to cause this d to change as well, quite obviously. Okay, but regardless of what's the change, right? This triangle is always formed. Okay, as long as A and B, right, have not reached the intersection yet. So therefore, this is our equation relating the unknowns, right? And we just do our implicit differentiation. Okay, so d dt in this case. So this is going to give us 2x, x prime, plus 2y, y prime, equals to 2d, d prime. Is that right? Okay, so clearly we can just divide the 2 away. All right, so therefore we get d prime, our unknown, is hence equivalent to x times x prime plus y times y prime divided by, let me see, divided by d. Chishan asks, is it minus x because it's in the x direction? Hold on, let me see. In the negative x direction. Yeah, actually that's a good point. Let me think about this. Okay, good point here, but you can actually treat x prime later to be negative. Okay, so if you want to put minus x here, actually you can. Okay, but I'm just going to treat x as the absolute distance. Okay, which means that this x distance here, right, has no, what do you call that? Has no direction. Okay, which means that minimum can only be 0 lah, cannot go negative. Right, but of course the rate can actually decrease, meaning to say x can actually decrease. Then that's when you input x prime itself to be a negative number. Okay, so let me demonstrate that. So once you have this, right, now of course this d is just given by x squared plus y squared. Okay, so therefore I get this same thing. I'm just going to copy and paste this guy here and replace the d by this guy. Okay, remembering my square root. So you can see that I know everything inside here, right? Because x and y are both given, and then x prime and y prime are actually given as well, because those are the speeds of travel. Okay, so hence, right, we have to take note, like what Jason mentioned just now, right? Actually, both x prime and y prime are negative. Okay, so let me just put, noting that, so at x equals to, let me see, so x equals to 60 meters. Oh crap. Okay, this one they give meters, then this one they give kilometers per hour, right? So I don't know, I'm just going to keep everything in kilometers and hours, all right? So that I don't need to convert so many things. So because this is 60 meters, right? So therefore this is actually 0.06 kilometers. Okay, because make sure our units agree. So therefore, y, right, is actually equivalent to 0.08 kilometers. And then your x prime. So x prime, this one, let me put a different color. So x prime, right, is actually negative, okay, 90 kilometers per hour. Is that all right? Okay, Kevin, later I answer your question. So y prime is actually equivalent to negative 100 kilometers per hour. Okay, so let me address Kevin's question at the same time. So this x and this y, right, is not like a displacement. You can treat it as a displacement if you want, okay? But you can treat it as a distance as well. So it's just a separation distance. But intuitively, we know that this A, when it travels towards the intersection, this x must be decreasing. So if the x is decreasing and x is a distance, right, then x prime must be negative. So decreasing at what rate? Of course, it decreases at 90 kilometers per hour. Okay, because this A is trying to cover 90 kilometers every hour, right? After 1 hour, you have moved 90 kilometers already. Okay, so therefore this x is definitely decreasing at the distance of this speed here. All right, so that's why I put negative 90 kilometers per hour here. Okay, the same goes for y, right? The same goes for y because y is a distance, right? And b is traveling towards this x, so reducing y in the process. So y must be negative 100 kilometers per hour. Okay, so that's one way you can look at it. Another way that, yeah, Kevin, that's correct. So another way you can look at it, right, is you treat x as a displacement. So if you treat x as a displacement, this is your 0 point and this x is towards the right. Okay, I mean, this is up to you. I mean, it's your definition. So therefore, towards the right is positive, then towards the left must be negative. Remember, I think I mentioned that, right? When x is towards the right positive, then when you differentiate x, right, v must also be towards the right positive as well. Okay, or rather your x prime, right, must be always towards the right positive. Because when you do a d dt, right, you do not change the vector polarity. Okay, so therefore, x prime must be towards the right positive. And in this case, 90 kilometers per hour is towards the left. So hence, right, x prime must be negative as well. Okay, so two ways you can look at it. You can treat it as a displacement if you want. You can also treat it as a distance. Both will give you the same polarity for x prime. Okay, so let me just return back to my distance notation. So hence, once you understand that, right, then you can just calculate d prime quite easily already. So of course, I'm not going to do that. So d prime, right, is just equivalent to, okay, so you plug in the numbers, you're going to get a negative answer. Okay, definitely it's negative. This guy is definitely negative, right? Because you can see from here, right? Positive times negative plus positive times negative. So this whole thing is positive, and then this whole thing is negative. This whole thing is positive as well. So therefore, you're definitely going to get a negative answer. Okay, so I leave you to compute this yourself in kilometers per hour. Okay, so common sense tells us that this kilometers per hour, right, is going to be more than, that means the speed at which A and B are approaching each other for this D prime, right, is definitely going to be bigger than 90 and bigger than 100. Okay, because you can imagine that this is moving here, right? So this is closing much faster, right? A and B is getting close to each other, right? Much faster than 90 and 100 respectively. Okay. So Nanyong asks, why is y negative if it is going up? No, it's not going up. It's actually going down. Okay, because you have to take a reference point here. So therefore, if you either use this, or let me just use another color to represent another possible notation, right? So as I mentioned just now, x could be positive in this direction. Okay, so therefore you treat x as a displacement. That means y, right, must be a displacement from the intersection as well. So this must be your y. So y is downwards positive. You see that? So upwards is negative. This downwards is positive y. Okay, rightward is positive x. So this guy must be negative. Is that all right? Okay, so if you look at this guy, right, let me just put a note here. So this is actually y prime. In both contexts, y prime is actually negative 100. Okay, same thing go with x prime. So x prime is going to be negative 90. Any objections? Let me just use the same color. Don't mess up. Okay. So you calculate, I'm like lazy. So therefore, let's move on. Okay, I think this is the last example for this part. Hold on, let me see. Okay, let me just push through another 5 minutes to finish up this example, and then we will take a break before we move on to linear approximations. We have a man walking along a straight path at a speed of 1.5 meters per second. A searchlight is located on the ground 6 meters away from the path and kept focused on the man. So let's try to draw. Okay, I'm going to draw the top view, right? So top view. So we have a path. This is my path. And this is my man. So man is here. Okay, let me see. So therefore, the man is actually walking along a straight path at a speed of 1.5 meters per second. So obviously this guy is 1.5. Then we have a searchlight that is located on the ground. Of course, the man is also on the ground. So this is a top view. So we have a searchlight. Let me use orange for the searchlight. 6 meters away. Okay, so this is my searchlight. And kept focus on the man. Okay, so this is my light. And I know that this guy is actually 6 meters from the path. So this guy is 6 meters. All right. So at what rate is the searchlight rotating when a man is 8 meters from the point on the path closest to the searchlight? Oh, okay. So which means after the man, right, reach here already. So after some time, the man walk, and then reach somewhere here. Okay. So when the man reach here already, right, this guy is actually 8 meters. So this distance is 8 meters. Okay, then we say at what rate. So now let's define our unknown here. At what rate is the searchlight rotating? So rotating what? Rotating must be what? Angle. Okay, so which means, right, we actually want, let's call the angle theta. So theta prime. Okay, at what rate is the searchlight rotating when the man is 8 meters? So which means if you look at this expression here, I mean this, the man is walking. So the searchlight is actually focused on the man, and this searchlight is going to rotate. Okay, so hence at 8 meters away is going to be this angle. So let's call the angle theta. Any objections on the interpretation? So we want this theta prime. Okay, as you can see, this, searchlight is going to turn clockwise, right, when focused on the man. So once we see this triangle, it's actually just a right angle triangle. Okay, then subsequently we can just use our basic trigonometry to form the relationships. So obviously the relationship will be this distance. Okay, so this distance, right, let me call this x once again. Right, so I know this is 8 meters, but let me just replace that by the distance x. And this distance will be 6. So 6 is a constant. Okay, so clearly we can define the relationship tangent theta is equivalent to opposite, which is x, over the adjacent, right, which is 6, always 6, so just constant 6. Okay, so once you have interpreted this, right, obviously we want our theta here, right? So you can do a tangent inverse, or you can just do implicit differentiation, right? So maybe it's easier to differentiate tangent in this case. So therefore, I'm just going to have d dt. So you're going to get differentiating of tangent, I'm going to get secant square. Secant square theta, then chain rule theta prime is equivalent to 1/6, is a constant, x prime. Okay, so therefore my theta prime here, I need to know. So theta prime is actually equivalent to 1 over 6, which is x prime over 6 secant square theta. Okay, so once I have that, right, then obviously x prime is just my speed of the man walking. So that's actually increasing at 1.5 meters per second, as you can see. This x is increasing. So x is increasing, right? This speed is also positive. Okay, so x prime is positive in this case. So I know x prime, no big deal, but I do not know theta. But I can always find out because I know this relationship already. Okay, so we can say that at x equals to, so we have at x equals to 8 meters. So we can solve for my theta. So theta is actually equivalent to, let me see, tangent inverse. So theta equals to the tangent inverse x over 6, right? But x is 8. So tangent inverse 8 over 6. Okay, so of course you can calculate your theta, and definitely you can substitute in here. All right, and x prime is known. So we can calculate this easily. Okay, so I'm just going to quickly write this here, and you can go and calculate yourself. So theta prime is equivalent to x prime, right, which is a positive 1.5 divided by 6 multiplied by secant square, this guy. Okay, so this theta prime will be in radians per second. Okay, of course this must be in radians. This theta must be in radians. All right. Questions? Okay, you have no questions. Let's take a break. Well, maybe I'll just calculate the values here and plug this in. So let's take a break till 12:15. So let's continue. Today we're going to continue to this applications 2 for differentiation. And first of all, we're going to look at this concept of linear approximation. Linear approximation. So linear approximation is actually extensively used. So what is linear approximation? Now, if you look at these figures here, you can see that when you get very close to the point at which the tangent is drawn, you get closer and closer. Now, if you get very close, right, you cannot even differentiate between the actual curve and the tangent line. Okay, so of course you must get close enough. Of course, how close is close enough? We have some what do you call that? Error analysis for that. Okay, as you'll see later, right? But I think the concept here is pretty clear. Okay, as you zoom in closer to closer, at which the tangent point is drawn, or at which the at the point at which the tangent is drawn, you cannot differentiate. Okay, between the curve and the tangent. So, therefore, right, we say now it is possible that we are able to get the f prime at a particular point easily. Okay, but however, it is possible that we are not able to get the function value here so easily. Okay, so when that happens, right, if you can choose the point, an appropriate point to draw your tangent, let's say, for example, in order to get the value of this point, right, I can actually draw the tangent very close to the point, and therefore my tangent line here approximates my curve well. Okay, so this tangent line, right, approximate this curve well, very close to this point x here, whereby I want to find the function value, then I can actually use the linear approximation. Okay, so this is the idea here. And this approximation is actually important because the most basic numerical technique, right, known as Euler's method, are being used to approximate solutions to many differential equations. And the differential equation is one of the equations that you saw previously, which is given by y prime equals to ky. Okay, you still remember we solved this, right? Whereby this differential equation is the one that is modeling exponential growth. So therefore, this is simple enough to be solved. But there are many differential equations that are slightly more complicated and we can't solve it exactly already. Okay, so therefore, in many cases, right, we use numerical techniques such as Euler's method to approximate the solutions. Okay, I'll give you a quick glimpse of Euler's methods in a while later after we understand this linear approximation. Okay, so moving on, right? So this is what I'm trying to say just now. Okay, so let's have an example here. Let's say, for example, f.6 is easy to find, right? But it's very difficult to find f of 0.605. Okay, so let's say you want the value close to this point, right? It's quite difficult to find. Okay, but from this drawing here, you can somewhat visually understand that this point on the green line can be approximated quite close to the point on the red line, as you can see from here. Okay, if you zoom in close enough. So therefore, why not we just use the linearized version, right, given by this L here, right, of this tangent curve to approximate the function value exactly. Okay, so therefore, we might not be able to get the exact function value, f of 0.605, but we can get pretty close to it. Okay, we can get pretty close to it if this 0.605 is close enough to 0.6. Okay, so indeed, this is the case here. So what is the linearization of f? Okay, what is the linear approximation of f? It is nothing new. It is just the gradient of the tangent line. We're just using the gradient of the tangent line. So you can see this point slope form of a linear equation, right? Okay, so you can observe that this is given by y minus y naught. So where is y naught? So you can treat y naught as your f of a. So let me just put a note here. Okay, this y naught and x naught is just this guy. So this is x naught, this is y naught. So if you treat a and f of a, right? So where is A? This is A. Okay, so therefore if you treat x naught is A, y naught is f of A, so therefore what is this? This is just y is f of x, right? So this equation becomes f of x, y is just f of x, minus f of A is equivalent to some gradient m, but gradient is f prime what? Correct? And this m, right, is actually taken at this point. So therefore, the gradient, right, is actually given by f prime. So slope is equivalent to f prime at A. Okay? So slope of the tangent line here, right, is actually f prime A. So indeed, this m is equals to f prime A. So therefore, we have m is f prime at A, and this x is just x. And what is x naught? X naught is A. Okay? X naught is A. So you realize that this is actually just a point slope form of the equation. Okay? And then just messing around with isolating your f of x or your y, you get this guy. You realize that? Just bring this minus fa across, right? So therefore you get f of A plus this thing. So this thing is just this thing. Observe that? Okay? So this y here is actually your f of x. Is that all right? Okay? Can, right? So first, this is a linear approximation because I'm just analyzing the tangent line. Okay? I'm analyzing the tangent line. So therefore, in reality, right, this is not exactly the same because you are actually looking at this curve instead, which is your y equal to f of x. Okay? So therefore, right, it will be approximately. Okay? Approximately. Of course, how good is this approximation really depends on the separation between this true value of f of x and the linear approximation. So by intuition, right, or deduction, you can clearly see that if this point or if this x is close enough to A, then this gap will be small. If this x is far away from A, then this gap will tentatively or normally be bigger. All right. So therefore, this right-hand side here, f of A plus f prime x minus A, right, is known as the linear approximation, okay, or also known as the linearization of f. Questions on the idea? Okay, so therefore this part, I should more accurately write it as approximately, okay, because we are looking at this blue guy here. So let me change this to y instead. So this is known as the linearization. So it's still talking about the same tangent line. Okay? So we need B to be close to A. And by the way, this point A is actually known as the expansion point. And why is it called expansion? I'll explain in a while. So let's look at an example first, okay, before we discuss further. So we want a linear approximation for the function, right, which is the cube root of x at x equals to 8. So at x equals to 8, of course, we know that the cube root of 8 is just 2, okay, so that's very straightforward. But the point here is use the linear approximation to approximate the value of the cube root of 8.05. So this demonstrates the example whereby it's easy to evaluate the function value at some point, A equals to 8, for example, but it is not so easy to evaluate the function value at nearby values, okay, for example, 8.05. So we also want to use this linear approximation, right, to estimate what's the value of the cube root of 25, okay, using this x equals to 8 as our expansion point. All right, so therefore, first step is just to get your f prime. Very simple, First step, just to get your f prime. Once you get f prime, then substitute the function value or the f prime value, right, into your linearization, and then you can perform whatever calculation given whatever point x. So hence, f prime x is trivial. So just bring down the cube root, which is your 1/3, and then 1/3 minus 1, you get minus 2/3. So therefore, you get this expression here. Okay, so the linearization, this guy, right, is actually just equivalent to this form. Okay, because we can calculate this, f of a is in fact 2, because a is 8. Let me just write here, where a equals to 8. Okay, now obviously this a value, right, you want to choose somewhere whereby the function value can be easily calculated at that particular point. Okay, so therefore cube root of it is easy, right? So hence we have this 2 here, and then plus 1/12, because this guy is actually 1/12. Okay, after you substitute a equals to 8, right, you will get this guy giving you 1/12. Then subsequently, this is your f prime, and then you have x, which is your unknown. So unknown is this 8.05. Okay, so let me just write here, this x, right? So you want this guy. So x is actually equivalent to 8.05. Later, you will sub in here. Okay, so the linearization is actually 1/12x plus 4/3. Okay, because it's actually 2 minus 8/12 here. Okay, so you should get 4/3. So once you have that, you can use this to calculate your linearized value, right, at x equals to 8.05. Okay, so therefore you have that, and then substituting in the value, you get, let me see, you get 2.004. Okay, so 1/12 times 8.05 plus 4/3, right, which is coming from here. So use this and this. So you get 2.004. Okay, 2.004. Then if you observe and compare to your calculator value, right, your calculator gives 2.004158. This is 416. So it's a very good approximation. Okay, and this good approximation is expected, right, since 8.05 is, or x equals to 8.05 is very close to a equals to 8, to the expansion point. Okay, so therefore, if you zoom in there, right, you cannot even tell the difference between the curve itself and the tangent line. Okay, so that's to be expected, the good approximation. However, if you use the same expansion point to do the cube root of 25, now your x is 25, but your expansion point is still at 8. So what are you going to get? You're going to get 3.4 for the cube root of 25. However, the calculator gives 2.92. So clearly this is not good. Okay, because you can see the difference here is actually 0.5, roughly 0.5. So 0.5 divided by the true value 3 here, right, is what do you call that, 1/6. So it's actually slightly less than 20% difference, which is not good. Okay, 20% error is not good, 15% error is not good, right? So hence this is poor approximation. Okay, because 25 is far away. Since x equals to 25 is far from the expansion point a equals to 8. Okay, so I think this effectively demonstrates the idea. Okay, so if you have very close to 8, just right beside here, this is good approximation. Okay, but this is bad approximation, as you can see this difference here. You see that? Okay, so question, how do you get a good approximation for cube root of 25? I repeat my question. Clearly, this cube root of 25 is lousy. Now my question is, how do you get a good approximation, a good linear approximation for the cube root of 25? Any guesses? Cube root of 27. Cube root of 27. Good. So which means what? Which means you choose point A to be 27. Okay, very good. So the answer here, choose the expansion point A to be equivalent to 27. Okay, so if you do that, right, you are going to get this calculator value or very close to this calculator value. Okay, then quite obviously, because, right, let me just extend this guy a bit to show you the thing. Okay, so let's say this is extended. So you can see you want to get this value, but if you choose 27, so I'm going to just estimate, maybe 27 is here. 27. So if you do a cube root of 27 and you linearize from there, let me just draw a line here to that. So you're drawing the tangent line at this point. So if you draw the tangent line at this point, right, it's going to be a very good approximation. Let me draw another tangent line. Okay, you can see, if you draw the tangent line at this point, this is my tangent. Okay, at A equals to 27. Obviously, this tangent is going to be very good approximation, as you can see here. It almost intersects this actual value for the cube root of 25. Okay, so let me prove it to you, and you can actually prove it to yourself as well. So therefore, the linearized equation is still the same. It's just that A is now changed. Okay, so therefore, just going to copy and paste here. So this is my linearized equation. Hold on. Oh, sorry, it's not. Because I need to calculate f prime. Okay. So let's do that. So we have 1 over 3 cube. 1 over 3. 1 over 3 x to the power minus 2/3. Okay. So let's calculate. We just prove it to you. So f prime x, right, is actually 1 over 3. Okay, let me just put 1 over 3 x to the power of minus 2/3. So what about your f prime of 27? Choose A equals to 27. So this is going to be giving me 27 minus 2/3. But 27 minus 2/3 is actually easy to calculate because this is actually 1/3. So 27 to the 1/3, right, is actually 3, right? 3 times 3 times 3. Okay, so it's 3. So it's actually 3 squared. So hence, it's actually 1 over 3 multiplied by 9. So that's actually giving me 1 over 27. Is that right? Okay, Anna. So therefore, f prime is actually 1 over 27. So hence, what's the linearization? So linearization of x is actually equivalent to, so f of a. So what is f of a? F of a is just 3. So cube root of 27 plus f prime, which is 1 over 27, multiplied by x, but x is 25. 25 minus a, 27. Is that right? Okay, so therefore, this is actually 3. Sorry, my cube root. Cube root is actually 3 plus 1 over 27 times 25 minus 27 is minus 2. Okay, so therefore, this is actually just 3 minus 2 over 27. Okay, so 3 minus 2 over 27, let's calculate that. So you get 2.926. Okay, so I'm just going to cut off at the third decimal point. 2.926. 2.926. Isn't this 2.926 very close to the actual value at 2.924? Observe that. So therefore, just choose a point that is close to the expansion point and you will be able to get a very good approximation. Okay, of course, choose this point A such, right, you can calculate the function value easily. Questions on the concept of linearized approximation or the linearization of f? Very good. So we're going to move on. So how does the calculator evaluate these two cube root values here? Actually, the calculator is using an approximation, but it is a higher order approximation. Okay, so this explains why that A, right, is actually called an expansion point. The reason is because this approximation is known as the Taylor series expansion. Okay, don't worry too much about this, but I'm just going to show you that Taylor series expansion is actually given. So Taylor series expansion of some function of f of x, right, is actually given by this form. So it's actually given by f of a plus f prime at a times x minus a plus f prime prime at a over 2 factorial x minus a square plus dot dot dot. I'm just going to give you the general formula. F differentiate n times at a over n factorial x minus a to the power of n. Okay, so therefore this is known as the Taylor series expansion. So higher degree approximation means you consider more terms. This higher degree, right? We are considering more terms. Okay, more terms. How many terms? I don't know, maybe 100 terms, right? More terms in calculator. Okay, so currently our linear approximation, only 2 terms. Okay, so therefore this higher degree approximation, right, is actually known as the Taylor series, and we are just using the first 2 terms of our Taylor series. Okay, if you are interested, you can actually calculate the quadratic term. So this is known as the quadratic term. So if you plus the third term here, right, it's actually using a quadratic approximation. Okay, so you can actually just go and calculate this term plus to our example just now, because we have the linearization already. So if you calculate this term and add to this linearization, right, you are going to get a better approximation. Okay, for example, in our cube root of 25 expansion about a equals to 8 just now, right, we didn't get a very good approximation, but if you get this term, it's going to be even better. Okay, so actually let me just draw a representation here. So what happens here is that you have your function. Okay, let's say this is your function. Then your linear approximation, right, is actually, let's say this is your expansion point. So then it's your linear. Okay. Then subsequently, if you do quadratic, right, you're going to get maybe something like that. Something like that. Okay. So therefore, this is when you have 3 terms. Let me try to draw a bit. So 3 terms. Then this one just 2 terms. Okay, then this one is your f of x. Okay. Okay, messing up here. Questions? Okay. Let me mute the guy. Okay. So moving on. So let's take a look at this example. Find the linear approximation of the function g of x equals to cube root of 1 plus x, and use it to approximate numbers 0.95 and 1.1. Okay, the cube root of these two numbers. So first of all, consider what a value that you want to choose. Obviously, the cube root of 1 is the best. Okay, because 0.95 is close to 1, 1.1 is clearly close to 1. So therefore, we just choose a equals to 0 because 1 plus a got to be 1. Yeah, which is here. Okay, because it's 1 plus x, right? 1 plus x, you want it to be 1. When the cube root of 1, you can calculate that easily. Okay, so therefore you just choose this x, which is your a, right, to be 0. All right, so therefore g of 0 is just 1. Simple. Okay, so once you have your a, which is 0 already, then everything else you just plug into the formula. So your formula, linearized formula, right, is actually given by 1 plus 1/3 x. Okay, so I will go through this part. It's pretty straightforward. Differentiate and then substitute in your value of a. Okay, so once you have that, right, then recognize that your x is simply 0.95 and 1.01 respectively, and then just substitute into the formula to get your expression. Okay, so you can see that 1 plus x is 0.95. Okay, apologies. This part, take note. 1 plus x is 0.95. So x got to be minus 0.05. Okay, x is not 0.95 itself. Okay, because we are trying to get this cube root of 0.95, and that happens to be 1 plus x. Okay, so 1 plus x equals to 0.95. So you get an x value, and then you substitute into your linearized approximation, you get the answer. Okay, so you just repeat the same for 1.1. All right. Questions? Looks good? So the essence of linearization here is always the same, regardless of what function you are trying to approximate. Okay, so another example, find a linear approximation of sine x at x equals to pi over 3 and use it to approximate sine 62 degrees. Okay, so we observe that actually at pi over 3, so this is actually your expansion point. So this is actually your a. And this a, right, is actually equivalent to 60 degrees. Okay, because it's pi over 3 radians. So therefore 62 is close enough to 60. So it's okay, right? So the approximation will be reasonable. So therefore, you just have to find your f prime as usual. So because your f of x is sine x, so f prime is just cosine x. Okay, so you substitute in your expansion point, which is your pi over 3, you will get half. Okay, because cosine pi over 3 is half. Then subsequently, what's your linear approximation? F of a. But f of a is actually f of pi over 3. Okay, which is sine pi over 3. So sine pi over 3 is actually square root 3 over 2. Then plus f prime, which is your half. Then you have your x minus a. A is your expansion point, pi over 3. Okay, so once you get your linear approximation formula, you can actually just plug this 62 degrees in radian form into the formula. Okay, and then press your calculator for the calculation. Right, and take note that because this part, right, you use pi over 3, which is a radian. So make sure you convert 62 degrees to radians first before you use your radian formula. Okay, because this part, right, you use a radian, so this part you must use radian. If this part you use degree, this part you must use degree. Okay, definitely. Right, the units must agree. Questions? So, look good. Moving on. So this is what a graphical representation looks like, right? So clearly you can see that this is your f of x equals to sine x, and then at pi over here, right? Pi over 3 is at 3.14 divided by 3, so it's about 1. Okay, so you can see here, right? So this value is sine pi over 3 is square root 3 over 2. So what's the tangent? So the tangent is this blue line here, okay, given by this linearized formula, expanded about pi over 3. Okay, so therefore, if you want 62 degrees, which is just slightly beside, so therefore it's clearly going to be a good approximation. So this part is 62 degrees. Okay, I'm just eyeballing this, of course. So therefore, this is very good approximation. Okay. Right, very close. So this is what linearization is about. And at the start of this chapter, I mentioned that I want to discuss a bit on the usage of linearization in this numerical method called Euler's formula. Okay, so I'm just going to complete the lesson here today by talking a little bit about what is this numerical method. So actually you have encountered numerical method before already. If you still recall, the first numerical method I think we dealt with, right, is your bisection method. Okay, because in many cases, if you still recall, we are not able to get the roots, or we are not able to solve a simple equation like x plus sine x to 2, for example. Okay, x plus sine x equals to 2. We can't solve, right? Because we cannot factorize out x easily. It's not a quadratic equation, it's not a polynomial. So therefore, we use this bisection method, right, which is just iteration. Okay, you bisect once, get some value, compare, bisect again, compare, and keep on bisecting until you get close enough to the root. Okay, or your f value is actually very close to 0. So the bisection method is a numerical method. So now, what is the Euler's integration method or Euler's method? Okay, so let me just show you Euler's method. So Euler's method make use of the linearization process. So let's say this is your function value f of x or your function f of x, and this is your x. Okay, so now let's say you are able to know what is the initial condition. So which means, right, at this, we call this x naught. You know f at x naught. Okay, you know f at x naught and you know x naught, but you don't know f of x. So what does this sound like? This sounds like a differential equation. Okay, so let me give you an example. Let's say in a differential equation, right, you know your f prime is going to be given by some function of x. Okay, let me just call this y. Okay, we are more familiar with y. Y prime is a function of x, y. Okay, but you do not know. That means you know this function, but you do not know what is your y. Let me just replace this by y. And let me replace this by y naught. Okay, so now you see, what's the example? The example here is previously, right, we have y prime is equals to ky. Remember, right? Y prime equals to ky. dy dx or dy dt equals to ky, right? Our exponential growth model, right? But generally, you may have something like that. Okay, that means you know the function of y prime, which is just this big F here. But you do not know what is actually the function y itself, and you want to find that. Okay, so objective is to get solve for y of x. You do not know this y of x, okay, and you want to solve from the differential equation, but you know y prime. So what's the whole idea? The whole idea is to use linear approximation. So what's the linear approximation? Simple. y1, go to y1. Okay, you want to get y1, or rather y at x1 is equivalent to what? Y at x naught plus a linear approximation, which is some change in x multiplied by the y prime at x naught. Okay, see, what is the y at x naught? It's just this number. Okay, that means I know what is my initial point. Then I want to go to x1, but where is x1? X1 is just maybe here. And what is this get? Change in x. Okay, so can I calculate this? Yes, I can, because I know this y prime. This is given. This is the differential equation is given. So I can calculate this y prime. I just multiply by this delta x, which is something that I decide. Okay, I want it to be small. I want it to be close to x naught. So therefore, let's say I can get my y prime, which is my gradient, and I project to x1 using a linear approximation. So what is this point? This is my y at x1. You see that? Okay, so if I call this y naught, and I call the green guy y1 in short, so therefore, what is my repetitive formula? Check. So let me just write down y1 is equals to y naught plus this delta x, right? I can call it h, usually we call it h, okay, which is just some small change in x, okay, same like your, what do you call that, limits. So therefore, h multiplied by y prime at x naught, right? So you can do this once, you can do this twice. Let's say you want to go to x2. Let's say you know the projection to x2, the gradient to x2, you can calculate that. So isn't this getting y3? Oh, sorry, y2. So of course you can get y2 is equals to project from y1 plus take a step, multiply by the y prime at x1. Okay, so I think you know where this is going already. What's the general formula? The general formula is yn plus 1 equals to yn plus h y prime at xn. Okay, so this is what Euler's method is about. It solves a differential equation, a first order differential equation using linear approximation. Okay, or successive linear approximations. So basically you do this. From here, project again. Then from here, project again. From here, project again. From here, project again. And so on and so forth. Okay, so what is the condition? What do you think is the condition? Before we end, let me just check with you on your concept understanding. What do you think is a good condition, right, that you need to have for this approximation, for this linear approximation to be close to the actual solution? So this is a linear approximation, but your actual solution maybe look like that. So this is your y of x. This is actual, or what we call exact. So if you want this jagged line, right, to be good and close to this exact blue line, what do you think is desired condition? Any guesses? No guesses? Continuous. What is continuous? I mean, in this case, your y of x will be continuous. Not only continuous, your y of x will be smooth. Okay, or else you cannot get y prime. So if the y prime is defined, that means y prime is a so-called function, some elementary function, for example. Okay, so therefore that function, of course, has to be continuous and smooth. So which means y has to be smooth, or else, right, it's not differentiable. Okay, so therefore this exact y, right, will be smooth and continuous. So now the question is, how do you make this linear approximation? Like, for example, the way I draw here, right, this linear approximation actually look very far from this exact, which means that look at your error. Error is pretty big. Let's say at this point, right, this is an error. So exact is this guy, which you do not know, which you might not be able to solve. But this is the error. This is what you approximate. So this error is big. So now the question is, right, how do I make this error E to be small. Change x to 0, Kevin. No, the expansion point actually can be anywhere. You can expand about anywhere. So let me give you a hint. Because you are doing linear approximation, okay? So exactly, smaller delta x or smaller h, okay? Smaller h. Because you can see that this gap is very big. So the bigger delta x or h is, you have a projection that is further away from the exact curve. You see that? Okay? So therefore, similar to linearization, you choose a h small. Okay, so if you choose a h that is small, right, then clearly you are going to get maybe something like that, right? You get like small approximation, then small approximation. You know, the gap is very small. So you can see this wide approximation, right, is able to trace this exact y of x, right, more accurately. Okay, so therefore you should choose a smaller h. And because this is a numerical method, right, so the formula is always the same. So what we do is we just use a for loop or a while loop, right, when we program this Euler's method, and we purposely go and choose a super duper small h here. Okay, so a small h or small enough h, right, usually will work well for most functions. Okay, because there are some functions, right, whereby a small h will not work well. Okay, but those are beside the point. So therefore, small h, right, is desired. Okay, similar to linearization. So a small h will usually give a good approximation. Okay, so this is Euler's method, right? It's just like bisection method, right? You just keep on, you know, repeating the same, what do you call it? The same code. Okay, so what is the code? The code is actually this. So this is actually my Euler's method here. Just this formula. Okay, so what do I need? I need my initial condition. This is known as my initial condition, x naught, y naught. So this is actually prescribed. Okay, this is known. Like for example, at t equals to 0 or x equals to 0, what is the value of y? Okay, usually those are defined by the actual conditions or physical conditions on the ground. Okay, then subsequently, you know your differential equation, but you do not know what is your actual function, then we just use Euler's method. Okay, so of course, Euler's method is just a very crude first order method, right? And there are higher order methods, just like our Taylor series expansion, okay, that can do this more accurately and give very close answer to the exact function itself. All right, so I'll stop here. I'll not talk more about the higher order methods already. Okay, so of course, this Euler's method is just to expand your expand your understanding on the linearization process. Okay, it will not be tested. Of course, I won't test you on this Euler's method. Questions? Attendance, okay. Okay, I'm going to open the attendance after this. So I think most of you have no questions. So I'm going to stop the lesson here. So goodbye. So in fact, I'll open the attendance.